Hello and welcome to lecture 12.1, where we are going to be talking about reference frames. In Goldstein, these are chapters 4.9, 4.10 for those who would like to learn more. So my favorite example of different frames is a platform train versus the train frame. And this is a particularly useful example when you're taking the train from Chicago to Evanston, where you are going between different heights and changing directions and slowing and accelerating. So this is a really good illustration of frame transformations. Of course, we wish we were taking the train every day or every other day, but given the pandemic, we are cooped up at home. So I apologize for the nice memories that perhaps this analogy will bring up. I hope we will be back into the train soon. In the meantime, all we can is use our imagination. So I will be using two different frames, the lab frame or the platform frame, where all of the coordinates will be denoted as regular x, y, and z. And I will be also using the train frame, where all of the coordinates will have the index relative to the train. So the origin of these coordinates will change its position as seen from the platform, and the position of the origin of the train coordinates will be moving. In our case, we'll just consider one-dimensional motion at first. It will be moving with the speed of the train, vt, and therefore vt times t will give us the position to which the origin of the train frame has reached as viewed from the platform or from the lab frame. So this is the lab or platform frame. From the point of view of the train, this looks a little bit different. So this will be outside of train. This will still be x. And then inside the train, we will have the same exact coordinates, xrel. But all of this is sitting inside the train on the wheels, and the train is moving with the velocity vt. And so there are two cases. Vt can be either a constant, which will be case A, or, as in case B, Vt will not be a constant. And we'll consider both of these cases. In the case of Vt equal to a constant, there will be no difference in the equations of motion because both are inertial frames, so that's spoiler alert. And in the case when Vt is not a constant, there will be inertial forces. So that will appear in the frame of the train because the train accelerates, and therefore inertial forces is what's going to be pushing you around. Like if the train is making a turn, you will feel like you're pushed in the opposite direction to the turn. Or if the train is stopping, then the inertial forces are going to push you forward. So let's try and consider case A for when the velocity of the train is a constant. So in this case, when we write equations outside of the train, our Lagrangian looks like a regular one for point mass particle. It's nothing but 1/2 m times x dot squared, so 1/2 mv squared. However, let's try to express this in terms of the train coordinates. So we're going to switch from x to x relative. So how can we do that? Well, we can write down what x is in terms of xrel, and it will be xrel plus vt times t, right? That's exactly how we're going to translate between the two coordinate systems. We're going to plug that in to x, and our Lagrangian will look like 1/2 m xrel dot plus vt squared. Now we're going to expand this, and we're going to get that we have 1/2 m x dot relative squared plus 1/2 mv train squared plus mv train times x relative dot. So we can immediately notice that in this equation, v train is actually a constant. Therefore, it doesn't really affect the Lagrangian, or rather, it doesn't affect the equations of motion. So we can throw this away, and we're going to be left with just these two terms. In order to make progress, let us prove a theorem. If our Lagrangian is some Lagrangian L0 plus dl1 dt, then L1, this extra bit, does not affect the equations of motion. That's great, because it means that we can throw this term away, because in our case of vt equal to constant, this is a full derivative of mvt times xrel. So let's try and see where this comes about. So how are we going to prove this? Well, remember that we derived Lagrange equations from the Hamilton's principle of least action. So least action principle tells us that our Lagrange equations are going to come from the fact that the variation of action, which is an integral from the starting point to the ending point of our Lagrangian in time, vanishes. So variation of that vanishes. And let us try and plug in L in here. So if we do that, then we're going to get variation of L0 dt, but we'll also get a variation of L1 with a substitution at T2 minus L1 at T1. And because our starting and the ending points of our trajectory are fixed during the variation, remember that, right? Remember that? Then it means that L1 at T2 and L1 at T1 will not vary. It will stay exactly the same. And therefore, the variation of them will vanish. So that means that variation of this term goes to 0, and so does the variation of that other term. And the reason for this is that the variation of the path does not affect its starting or ending points. And so because these points are fixed, therefore the variation at these points vanishes. And hence this variation goes away, and we are left with the variation of the original, and the new Lagrangians are going to be the same, which has proved our point that this extra bit dl1 dt doesn't really affect the equations of motion, because equations of motion only care about what's left here in the variation principle. So that's awesome, and that means that we can throw away this term. It doesn't affect the equations of motion, so we can throw this away, and we can therefore write down our Lagrangian as simply 1/2 mx dot rel squared plus ddt of mv train times x rel, which is this term, and I'm rewriting it here explicitly for clarity, and then this term goes away because it does not really affect our equations of motion. So as a result, our equations of motion is going to be just due to this term, x rel double dot is equal to 0. That is in the absence of external forces. So it's exactly the same. As if the train were not moving. So this sort of frames are called inertial frames. It's a frame where the Lagrangian has this form. So if a body in the absence of external forces keeps moving at a constant velocity, then it means it is an inertial frame. So inertial frame is where the Lagrangian takes this form, or where bodies in the absence of external forces move at constant vrel, at constant velocity. So let's try and see what happens when our frame or our train starts moving at a velocity that changes in time. So if our v train is not a constant. Let's figure it out. I'm going to see you then, and please don't forget to do the quiz. Hello, and welcome to part 2 of lecture 12. Where we're going to continue discussing reference frames. And now we're going to consider case B. When the train velocity is not a constant. So if we were to illustrate this graphically, we could say that from the point of view of the platform train, our train goes along some weird trajectory, and the train velocity depends on time, and it changes in time, so it's not a constant. So let's write down the Lagrangian as before. Lagrangian is equal to 1/2 of mx dot squared. So as usual, in the lab frame, we can always write down Lagrangian like that. And of course, we're going to plug into here the expression for x in terms of xrel. So that would be x is equal to xrel plus vt. So if we take the dots, x dot is equal to xrel plus the velocity of the train. And what we can also do is we can write it down in the vector form. So all of these are going to become vectors. So this is going to be a vector, and all of these are going to be vectors. So this is going to be a vector, that is going to be a vector, and this is going to be a vector as well. So then we can continue this expression over to here, and we're going to be able to write down that L is equal to m over 2 times x rel dot plus v train squared. As before, in case A, we can expand this into m x, oh, and this should be x rel dot squared plus m over 2 times v train squared plus m x rel dot times v train. So as before, we can actually throw this one away, and that is because it doesn't depend on either the coordinates or velocities. It only depends on time. And because it only depends on time, right? Vt only depends on t, doesn't depend on xrel or xrel dot. That means that it won't enter the equations of motion, where only derivatives of L with respect to x dot rel or x itself, xrel, will appear. Therefore, this term will not contribute to the equations of motion. And moreover, this term can be rewritten by forming the full derivative. So let's see how that works. We will keep this term in the same form as before. We will form a full time derivative over here. And then we're going to subtract off whatever terms we've added here, right? So we need to subtract off the other term with the dot. So it will be m xrel times vt with the dot. And we know that this term will not matter because it's a full time derivative. So it will not affect the equations of motion, and thus we're left with just these two terms. So the equations of motion that come out of here are going to be the momentum is going to be equal to dl dx dot rel, so it will be just the regular expression for the momentum. And the equations of motion, therefore, will be ddt of this, so it will be p dot, equal to dl dx rel. And you see dl dx rel, or in this case, yeah, it actually should be xrel. I don't know why I wrote rl. Guess I'm trying to switch to the r notation. So dl dx rel is going to give us minus m v, let me write it the same way so it's not confusing, m vt dot. Or in other words, this is acceleration, So we can write it out as minus m at, where a is the acceleration of the train. So what we have is, this is the inertial force, F equals to minus ma of the train, and so this inertial force is what pushes us back. This is precisely the forces that swing us side to side when the train turns, or push us forward or backward when the train stops or accelerates. The interesting corollary of this is that if the acceleration is a constant, it behaves just like gravity. And this is what led Einstein to postulate that force of gravity could be considered just like a non-inertial force. So in this viewpoint, mass warps the space-time. Well, that's great. We packed a lot of this here. Let us take a look at case C. What would be case C if we already considered an inertial frame, a non-inertial frame when the velocity was changing? What else is left? Well, here the velocity was changing, but the car of the train, actually, contrary to what I mentioned as an example, the car of the train wasn't changing the direction. It was always going forward and kind of moving sideways or slowing down or accelerating. Whereas in this case, we're going to consider rotation. So as an example of such a frame, you can consider a carousel or a merry-go-round. So let's draw a cartoon that illustrates the problem. So suppose that our rotation happens around the z-axis. So our omega is equal to omega scalar times z hat. So if we have a vector r, then its tail end is going to be tracing out a circle, and it's going to be maintaining a constant angle theta with respect to the rotational axis. So if we wait for a period of time delta t, then the tip of this vector is going to move by delta r. Where we can say that delta r, the length of this extra vector, is going to be equal to, so you see we will rotate this vector around a circle of radius r times sine theta, right? And let's denote this as r rel, because this is a vector that is measured in the rotating frame. So delta r in the lab frame will be r rel times sine theta times omega dt. So that will be the length of this little orange vector. And if we want to write out it in the vector notation, right? So delta r will be pointing into the board. So what will it be? So this delta r vector is going to be pointing in the direction perpendicular to both omega and rel, right? So it will be pointing in the direction of z cross rel. So z is vertical, rl is like that. So the cross product will be pointing to the board, and the length of this will be just rl times sine theta, right? That's the cross product between the two vectors, so we have the correct length, and all we need to do is multiply this by omega and dt. So this is how we can go from the scalar relation to the vector relation. And then we can say that certainly we can take omega and put it over here. Omega scalar times z hat is just omega vector itself cross rl, and all of that multiplied by dt. So from the point of view of the inertial frame, our Lagrangian is L equal to m over 2 times v squared. So if we were to try and switch from v to vrel to the velocity as viewed from the rotational frame, how can we do that? Well, let's try and switch from v to vrel. We can definitely do that using this relationship, because delta r over delta t will give us v. So this will be v times delta t, right? So v is equal to omega times rl for pure rotation, but for rotation plus motion, it will be v is equal to omega times rl. So that will be rotation plus any other motion relative to the rotating frame. So this allows us to switch between the velocity as measured from the point of view of the rotating frame to the velocity as measured from the point of view of the inertial or the lab frame. Hello, and welcome to part 3 of lecture 12, where we will continue discussing rotating frames. So we just figured out how to connect the velocity in the lab frame and in the rotating frame right over here. And now we will be able to use that relationship in order to obtain the equations of motion in the rotating frame. The first step to do that is we need to express the Lagrangian in terms of the coordinates and velocities as viewed from the point of view of the rotating frame. So, how we do that? Well, let's write down what the Lagrangian is, first in terms of the lab frame coordinates and velocities, and that is 1/2 mv squared. Now, having here obtain the relationship between v and vrel, we can therefore write that this is equal to 1/2 m times v relative plus plus omega cross r relative, all squared. So now we can expand all of that, and what we're going to find is that it is equal to one half mv rel squared plus m times v rel dot omega cross rl plus 1/2 m omega cross rl squared. So let's try and work on this a little bit. Let us do a little bit of computations on the side. So if we have a vector A dotted into B cross C, that will be equivalent, if we do a cyclic transformation here, so we're going to push C out from the right, it will come back on the left, it will be C dot A cross B. It'll also be useful for us to know that, of course, because dot product is symmetric, commutes, it will be equal to A cross B dot C. So let's keep this here. So if we use this relationship, actually the first one, and apply it to this term, we're going to get that this is equal to RL dot VREL cross omega. There is another term that we need to work on, and it is this one. Let's compute what differential of this is, because the reason why we did this is because when we take dl dr rel, rl was hiding here in the cross product. Now we have freed it up. So when we do dv drl, we can easily take the derivative. Now when we do dv dl drl, rl is hiding underneath here inside of the cross product and the square, so we would like to free it up. How can we do that? So let's compute what the d of omega cross rl squared is. So let's use the chain rule here. So this will give us 2 times omega cross rl dot d of this time omega times drl, and let's now use the chain rule where this will be A and this will be B cross C. So now let's make use of this last relationship here, so that we will group A and B together and dot it into C. So this will give us 2 times A cross B, omega times omega cross RL cross omega, and all of that is going to be dotted into DRL. So what we've done, we've freed up the coordinate here such that we can compute DL DRL easily, and this is exactly what we've done here as well. So let's do it. Let's compute dl drl, because that's what enters the equations of motion. dl drl is, this is the first instance of RL, so when we take a derivative, RL disappears. So it will be mass, let's factor it out, times VREL cross omega. That's this term, plus that term, plus this term. So 2's will cancel out, And what we're gonna get is plus DRL goes away, and we're getting omega cross RL cross omega. So that's the right-hand side part of the equations of motion, and the left-hand side part will involve the momentum, PRL, which will be dl dv rel. So let's compute that. So the first term contributes mv rel. The second term contributes m omega cross rl. And the last term doesn't contribute because it doesn't depend on the velocities. So that's great. So now we've gotten PRL. So what about the equations of motion? Well, from here we can write down what the equations of motion are. So it will be d dt of PRL is equal to dl drl. So d dt of PRL will be m v dot rel plus the time derivative of this will replace rl with vrel plus m omega cross vrel. And so this is dp rel dt, and now all of that is equal to the right hand side, which is just that, right? So this will be m times vrel times omega, or rather cross omega, plus this term, plus m omega cross rl cross omega. And as you can see, there are two terms that have the same exact form, so we can group them together. So we can cancel m and we can write v dot rel is equal to minus 2 omega cross vrel minus omega cross r. This is going to be Coriolis force, or rather acceleration in this case, and this is going to be centrifugal acceleration. Now let's try and obtain exactly the same equation of motion, but in a simpler Goldstein way. So how do we approach that? Well, over here on the left, we have derived the relationship between the velocities in the lab frame and in the train frame. Namely, velocity in the lab frame is equal to the relative velocity plus omega cross the relative distance. And let's denote this as equation 1. So what we can do with this is we can rewrite this in terms of derivatives of r. So this is equivalently dr dt is equal to dr rel dt plus omega cross r rel. And equivalently, this can be viewed as an equation for transformation between r and rl. This is how the radius vector transforms. So it's a transformation of vector r. Now we could write the same thing for any other vector xi. D xi dt is equal to d xi rel dt plus omega cross xi. So this will be transformation of vector xi. Okay, that's good. So what can we do here? Well, let us try and go one step further. Since this relationship works for any vector, and I forgot the rel over here, then therefore we can write in general that d dt in the lab frame will be equal to d dt plus omega cross in the relative frame, in the rotating frame. So this is the derivative in lab frame. And this is the derivative in the rotating frame or in the train coordinates. So we can now use this to convert equations of motion from one frame to the other. So let's apply this to our equation 1. So we're going to apply this to that equation. What will happen? Well, our equation of motion in the lab frame is that dv dt is 0, right? So, but ddt in the lab frame is this in the train frame, so it will be ddt plus omega cross, and then this will be applied to the velocity expressed in terms of the train coordinates in the train frame, right? So it will be v relative plus omega cross r relative. All right, so what do we get out of here? We are going to try and get equations of motion. So 0 is going to be equal to ddt will be v relative with the dot. Then we will have term omega times v rl, and ddt applied to this term will give us exactly the same term. So we will have 2 omega cross v rel, and then there will be term ddt. Let's see, there will be term omega cross rl. So there will be term like that. And just as we showed here, this is minus the Coriolis acceleration, and this one is minus the centrifugal acceleration. And let me demarcate the boundary here. All of this is, of course, equal to 0, just like here. So now let's try and then write down what the equations of motion will be in the rotating frame. So in the rotating frame, we're going to get that m times a is going to be equal to, and we're dropping all the relative indices because now everything is in the rotating frame. F effective, so the sum of all of these extra forces that correspond to these accelerations, so the Coriolis force and the centrifugal force, is going to be F effective, which is the sum of the physical force plus these fictitious forces minus 2m omega cross v. So that will be our Coriolis force, and minus m times omega cross r. So that will be the centrifugal force. So let's write that out explicitly. So this is F Coriolis, and this is F centrifugal. And we can massage the centrifugal force a tiny little bit in order to maybe make it look more like the form that we used to. What we can do is we can use another one of those vector relations. Let me write them out. Let's see where I can squeeze them. I can write it out over here. So if we have A cross B cross C, it will be equal to B back minus cab. It will be B A dot C minus C A dot B. So if we use this here, then we're going to be able to write that this is equal to minus M times, so this will be ABC. So it will be BAC omega times omega dot R, with a minus sign, minus sign, and then it will be C, so it will be R times A dot B, so it will be omega squared. So you can recognize here the centrifugal acceleration omega squared times R, and this is an additional term when omega and r are not perpendicular to each other. So now that we have figured this out, wrote down the equations of motion, let us now consider a couple of examples where Coriolis and centrifugal forces play a role and get an intuitive understanding of what they actually do. Thanks for your attention. Don't forget to do the quiz, and I'm going to see you in part 4 of lecture 12. See you soon. Hello and welcome to part 4 of lecture 12. Where we're going to be discussing examples of Coriolis force. So suppose that we build a hut at the North Pole and we're coming out with a baseball ball and throwing it out. So let's look. This is going to be our North Pole. Then there's going to be Earth rotating around it with omega Earth. And when we throw out the baseball, it's going in the lab frame, the one in which Earth rotates, baseball is going to go straight out. That is going to be the trajectory. However, if we jump into the Earth's frame, so if we jump into the Earth's frame, because Earth is blue, so let's draw it with blue. So if we jump into the Earth's frame so the Earth doesn't rotate anymore, then what will this trajectory look like? Well, one way of thinking about this is that in the Earth's frame there's going to be a Coriolis force. And this Coriolis force is acting in the direction of omega cross v with a minus sign. So v is going that way. Omega is going to be pointing at us, right? Counterclockwise means it's at us. So omega cross v is going to be into the board, but minus omega cross, so omega cross v is going to be omega sticking out, cross v is going to point up, but acceleration is minus that. So it's going to be deviating the trajectory in this way. So this is going to be our trajectory in the Earth frame, or in the train frame, or in the Earth frame. I don't know why I'm using the quotes for this. So that's what we expect. So let's try and find what the angular deviation of the trajectory will be. So for that, we know that there is a constant acceleration. So for that, we know that there is constant acceleration operating. And if there is constant acceleration, then this distance, d, is going to be acceleration times time over 2. And in this case, a is equal to Coriolis acceleration. So if we were to therefore look at delta theta, at the angular deviation of our trajectory, it will be d divided by v projectile times t. So that will be this distance, v projectile times t. So that is the angular deviation, and it will be given by a Coriolis times t squared over 2 divided by v projectile times t. So let's see, what is a Coriolis? It's going to be minus 2 omega Earth times v projectile times t squared over 2, and all of that is going to be divided by v projectile times t. So let's see which kind of terms we can cancel. So one of the t's gets cancelled out, v projectile gets cancelled out, 2 cancels out, and we end up with minus omega Earth times t. So this angular deviation is omega Earth times t, and the minus sign is telling us that it's deviating in the opposite to the positive direction of rotation, means it's rotating clockwise if the Earth rotates counterclockwise. We can actually understand this result intuitively, because if we take the lab frame perspective, then the trajectory of our projectile is a straight line, but Earth rotates under it by this angle in time t. And so this will be precisely the angular deviation of the Earth under the projectile. So suppose that for time of 100 seconds, our projectile travels before it loses altitude and falls onto the ground, what will be the angular deviation in this case? The angular frequency of the Earth is 2 pi divided by 24 hours, or 2 pi divided by 86,400 seconds, or cancel in 2 pi and 8-ish, we're going to get maybe roughly 7 times 10 to the minus 5. 1/second, radians per second. So the angle that we're going to get in the end over 100 seconds will be roughly equal to 100 times that, so it will be 7 times 10 to the minus 3 radians. Or, because 1 radian is around 60 degrees, so it will be roughly 0.4 degrees. And just to recap, the physics in the lab frame is that the Earth is rotating under the trajectory. So let me write this down, is that if we wanted to understand this in terms of our intuitive picture in the inertial frames, is that Earth while this is not a huge deviation, it would be larger for longer time of flight. So important for In the next part of this lecture, let's consider another example, in this case, of hurricanes. Don't forget to do the quiz. See you soon. Hello and welcome to the last part of lecture 12, part 5. We're going to talk now about hurricanes. Hurricanes are pretty awesome and scary. In fact, the equivalent of hurricanes in the southern hemisphere is a typhoon. And the two are actually qualitatively different. And the key difference in the physics is the Coriolis Force. Why would Coriolis Force behave differently in the two hemispheres? Let's try and take a look. But before, let's try and get an idea of how hurricanes come about. Where do they appear? I'm not an expert in hurricanes, so I'm kind of channeling what I read up online and saw in Goldstein books. So you can take a look there and search for yourself. But the basics, as far as I understand them, are as follows. Hurricanes form in several steps. So let's look at step 1. So I will schematically draw the US. Then there is South America, so that's kind of the coastline. Then there is Africa somewhere here. And the hurricanes start in Africa, then they cross the Atlantic, and then they approach the US. So as they do that, and they reach the warm waters, then in step 2, warm water heats up air. Hot air and moist air, hot moist air rises. encounters cold air, rains out, and releases latent heat. So when something condenses, it releases heat. In order to evaporate something, you need to give it heat. So in this case, once the vapor, water vapor, cools, it condenses, and then once it forms the droplets of water, it can rain out. So that condensation releases heat and creates even more updraft. So once that warms up the air even more, causes the air to rise, and because air rises, there is a suction effect, so the pressure at the bottom drops, and that pulls in even more air. From the ocean surface, and now we have closed the cycle that this air gets heated up and goes around like this. So that is how we get the air in the updrift going. Now we will have step 3. I guess I can move to step 3 over here. And the step 3 is the most interesting and relevant one. So if we look down the barrel of this column of the air, what we have is we have low pressure surrounded by high pressure. Low pressure because of the suction effect, and high pressure is around this column because there is no suction effect. So when you have a pressure gradient, it means that there will be flows from high pressure regions to low pressure regions. So there will be a flow like that, there will be a flow like that, and like that. But because we are living on Earth, hurricanes occur on Earth, and Earth rotates, that means that these trajectories will be curved. And as we've seen, the trajectories are curved to the right. Like on the North Pole, trajectory curves to the right. So here, trajectories will be curved to the right as well. That means that we have now gotten rotation that is counterclockwise. This means that the Coriolis force causes these updrifts, which are thermally launched, to rotate counterclockwise. And that is solely due to the effect of the Coriolis force. So air moves from high to low pressure regions, becomes deflected by the Coriolis force, and this deflection happens to the right. And all of these deflections to the right result in counterclockwise rotation. So from here, we make the conclusion that hurricanes rotate counterclockwise. Note that for typhoons, which is the equivalent of hurricanes in the southern hemisphere, the effect will be the opposite. They will be rotating clockwise. That is because the direction of omega relative to the up direction is flipped in the southern hemisphere. That's why the direction of rotation of typhoons is the opposite to that of the hurricanes. They rotate clockwise. So to recap, in the southern hemisphere, the analogs of northern hemisphere's hurricanes are called typhoons, and typhoons rotate in the clockwise direction. That's because Coriolis force points in the opposite direction. Namely, it deviates the trajectories leftward. There are other examples of Coriolis force acting on large scales in the Earth. For instance, rivers tend to push to the right, and so the right shore, as viewed along the flow of the river, is more eroded than the left shore in the northern hemisphere. So you would be thinking, why would Coriolis force ever matter? And here are the examples of when Coriolis force is making a huge difference on large geological scales. Thanks a lot for your attention. I'm going to see you in lecture 13, in which we're going to discuss energy in reference frames. Bye. Don't forget to do the quiz.